Any constructive criticism for our industry. It's all with good intentions. Let's dive right in. Okay, working assumptions. The interaction between the ocean and the atmosphere sustains our climate. I think we are all aware of that. Phytoplankton generate about half of the Earth's oxygen and regulate the temperature. Healthy fish populations play a crucial role as contributors of nutrients and plankton grazers in marine ecosystems. Recent scientific research finds we can create an ocean renaissance for wildlife by 2050 if we just let things recover on their own. Reducing the fishing pressure through sustainable aquaculture is a key part of this strategy. And many coastal spawning habitats are under pressure from mining, aquaculture, agriculture runoff, and urban expansion. And everybody that lives in this area knows that. So the presentation is RAS, the human factor. So how did we get here? For centuries, seafood came simply from aquatic animals, hunters, fishermen. World population growth and shrinking supply forced fishermen to become farmers. Contamination exacerbated ocean depletion, pushing fish farming to become an industry. Today's stunting of many of our industrial fish farming sites is pushing us to basically either go further offshore and or produce in RAS on land, or a hybrid of both. The situation with the cages, I think a lot of you are aware of it. There's no need to go through all of these. But the way I look at it is that the carrying capacity of the cultured water bodies basically doesn't comply with standard limnology models for nutrient thresholds for eutrophication. It's usually much lower than that in reality. It's not practical to model the biological dynamics of native fish, bacteria around the cage sites. There are many interactions, complex dynamics, which always seem to surprise us and bite us in the ass, as they say. Hydrodynamics of cages, especially large ones, and there's been a trend in Chile and Norway to go to larger and larger cages for economy of scale, presumably, and that doesn't seem to be working as well as it was planned. Most cage sites sit in very basic pH, and that's a problem with ammonia. And reducing drag of systems in the open oceans while also looking for increased flushing in the cages are contradictory to each other. So what drives the RAS evolution? Basically, like we said, ponds, raceways, and cages, while they're a very important source of the seafood, they can't expand very much anymore as the low-cost producer. They require very specific conditions, which are many times not stable. And RAS has matured to a point, as Alejandro was saying, that we can do it economically if it's done right and competitively. With the recent pandemic, we all know no country wants to rely on imports, and everybody's looking for a way to produce locally. So now RAS is a necessity, basically. It's not just a new technology, new exciting technology. There are many designs out there, many different systems, many companies. As Matt was saying, there are hundreds of projects declared. It seems like there's a new one every day. And there are many dilemmas about the scale versus risk, the shape, the filtration methods, and so on. So what is the promise of RAS? RAS can produce, it's a generic term, like I said, for many types of systems, many types of species, operating crews. So it's very hard to pinpoint exactly what RAS is, but there are some commonalities. The other thing that RAS encompasses many other activities around the RAS, the production itself, like the processing plant, the fish meal plants, the wastewater treatment, byproducts, and so on. And it is possible for RAS to live up to its potential. and I say that from experience, to its financial and environmental potential, but it's not inherent in any technology. You can't buy it off the shelf, unfortunately. Not at this point. Okay, a little bit about the design. I won't go much into it, but there are different approaches, different camps about how to design the RAS system, the best RAS system. I really won't go into it because time is short. But there are some critical design concepts that apply to all RAS systems. Oops, sorry. We're all looking for a low head flow design to use less energy to move the water around between the filters and the tanks. Solid removal, which doesn't make the solids smaller. We basically don't want to end up with the solids being dissolved in the water and creating more BOD and more bacterial growth. Robust biofiltration with a lot of extra capacity. Degassing systems that are efficient in energy. Again, CO2 is the main bottleneck for RAS designers, how to get the CO2 out of the water efficiently. And that makes us exchange the water many times more per hour per day just to get the CO2 out. Oxygen dissolving systems, which eliminate the risk of nitrogen supersaturation. Minimum requirements for ozone or disinfectants. I know they're promoted by many people, but they do tend to be a little bit of a double-edged sword if you don't use them in the right place. And built-in practical harvest systems. All right, this would be the ideal kind of scenario. Again, I'm trying to rush here, but generally only about 30% of what we feed ends up as fish, and all the rest ends up as some form of waste, whether it's CO2, whether it's nitrate, nitrogen, whether it's BOD. And so we need to address that. And we need to try to use the advantage of having everything concentrated under one building and coming out of central pipes to reuse all those wasted nutrients. And that's really the potential of RAS. Okay, there's the good, the bad, and the ugly. Generally, I don't have time for everything, but densities are high, and that's, I guess, good. You need a small footprint. You can control many of the parameters, but it seems the more you control, the more you don't control. Reduced labor if you design it right. Again, the market advantage of being close to the consumers, the ecological aspects of RAS, the advantages of being able to reduce organic nitrogen to nitrates and carbon to organic carbon to CO2, and the biosecurity aspects. However, the same points apply on the bad slide as well. High fish densities demand very efficient oxygen systems, and when you're putting a lot of oxygen in the water, you get a lot of off-gassing of different other gases that are in the water, and you have to deal with them. You need to know what you're doing. Controlled conditions. You can control some of the things, but for example, the bacterial fauna is very hard to control. It's very hard to understand. So we're just at the beginning of our understanding of what's really going on in these systems. The mechanical part is the easy part. Reduced labor. You have to keep really quality labor. You can't have anyone working there because one mistake can cause you a loss of a tank, a loss of a system. Human error is a huge factor. Biosecurity. Nothing is really fully biosecure ever. And the ugly, capital investment in RAS is high. Cages are starting to be on par, but it's still high. And that's one of the challenges we have to deal with as RAS designers. Operating expenditures can be high if it's designed wrong or operated wrong. Human error, as I said, complex systems. You can't have anybody just walking around there touching things. And the image that we're starting to see with Atlantic Sapphire about animal cruelty, swimming in their own waste. We've all heard these types of fear and pain and all kinds of other declarations that we hear in the media. So the paradox is, for RAS, everything is under control, which is good. But, of course, everything is under control means we have to control it. We have to be on top of it. And if we're not there to be on top of it, it's not going to fix itself. Some of the complexity of what a manager needs to deal with every single day in a RAS system. Many feedback loops. When you do one thing, you can't really forecast what kind of effect it's going to have, cascading effect it's going to have down the road. And everything ends up as feed conversion. So again, not much time to go into that. The processing plant, just a short slide to mention that in the end of the day, we talk about RAS and RAS and RAS, but the product quality is ultimately defined in the last week, if it's purging that's required, or in the last minutes, really, in the processing plant. One of the, again, there's the promise and there's the challenge. RAS can give us unprecedented freshness of raw material to produce pre-rigor products, which we can't really achieve in any other system, culture system, but the plants need to be designed, adapted. Technologies are not there yet for RAS raw material. The long and winding road to harvest, or even to break ground in this case, there's a lot of steps that need to go through to start a RAS facility. And many of the hundreds of projects that Matt mentions will not find financing and will never end up here. That's the reality. Okay, so 2 minutes more, Jairo. Recirculation systems, managed correctly, hold enormous potential for environmentally friendly grow-out to support more efficient cage farming. The industry today faces major management breakdowns, as we've all heard on the news. And that's because we're trying to scale up too quickly. And basically, I say it's a hot air balloon of hype just to get the financing. That's not the reality. The reality is we have to build it up slowly and stably. And what the industry needs now are more smaller, and many more success cases. And the last slide, this is our system. This is the system we've been working on and developing secretly, or the first ones to see it. Basically, we're trying to take all the my experience, my colleagues' experience, decades of experience with RAS, all the failures, basically, we've killed enough fish, and put them into a system that can be profitable, that can be practical to operate, and is a lower risk. So as I said, it's designed by engineers with a lot of experience, lowest market capex per kilogram. We already know that. The horizontal integration from stock to truck. So this one is a salmon project for 500 tons a year that goes from the eggs all the way through the processing, all in one module. The basic platform can be adapted to different commercial species. It's designed for low energy usage and on-site production, biosecurity, and risk diversification. So we don't have a big project that can all fail at once or can all burn down at once. These are smaller projects that are sitting closer to the markets. And it's very intuitive to operate. And some of the key data, 3,500 cubic meters of water, feed loads of 0.5 on average to 1.2 kilos per cubic meter a day. Requires about 8 people to operate. The plant is fully automatic, the processing plant. Makeup water, all it needs is about 25 to 50 GPM, so it means it can be installed almost anywhere or many places. Energy consumption of 4.5 kilowatts per kilogram. It includes a denitrification system, a feed storage, processing plant, backup generator, auto feed system, O2 and O3 generators, harvest and purge system, and office and control room. Okay, so thank you very much for your time.
Thank you, Yedod, for your presentation.